Okay, so this is the picture. That's the lemma, and that's the book. Okay, so the idea is to, okay, if you want to show that two functions are the same, it suffices to show it that homomorphic function that they are the same on a on this half line where it has the combination points. So we show that phi alpha W equal to phi delta W. Here the bisector is for W is equal to e to the I or minus I alpha plus beta over 2 times S and FB. So yes. Modulus of W begin. Yes. And so the idea is it is that okay, so with this W here, and we want to show that this integral over this line is the same as integral over this line. And so what we do is we apply Cauchy theorem to so we pick the distance R, where R will go to infinity, and we consider this for Johan. So we consider this path here. Let's call it the lemma R. So so 0 is equal to the integral over lemma R of the homomorphic function, which is f of z, and e to the minus 2 by w z, okay, yeah, here I need the z, not z, but by Cauchy theorem, and this is like the integral over gamma alpha R, say, so here, minus the integral gamma beta R plus the last integral eta R, where eta R is R to the circle, and the integral equal eta R on that by that. So I guess it's that R is equal to R times let me just read this notation. E to the IT. Okay, so this is like the integral between alpha and beta and alpha R T, and then minus Y W R I T, and then here we have R I T. T. We don't need anything sophisticated because we're going to take the modulus inside. And so what we get is so we take the modulus inside, and then we use the growth of the function, which is constant times e to the pi a r, I guess. Then we get r, and then we get e to the minus pi, and then we get the real part of w times. Okay. So the only thing is this one, but we have that if okay, when you consider the real part of W, which is like the modulus of W, and here we get the cosine of R, that's the over 2. I don't know why that's minus. Because there is a line. So here we have the minus. That failed. But T ranges between alpha and beta, so that's less or equal than and so this is the e to the pi r, and then we get let's even a 2, but here let's put it in a minus, so we will have this one, and so we get modulus W, modulus W sine of. Okay, so this cosine at most is the cosine of beta minus alpha over 2. That's because of G. It's between alpha and beta. So this is between cosine alpha over 2 and cosine beta over from the cosine alpha minus beta, cosine beta minus alpha. Worse than and get minus R A over. Okay, and that goes to 0 times R. Anyhow, so this goes to 0. This R is going to be provided that this number is positive, so provided that W is bigger than A to the 2 over of data. which, by the way, in this picture, it is what we expect, because if you do the geometry, it is that's alpha, that's beta, that's minus alpha minus beta, and then it is so. So this length here is exactly that. Yes. So provided the quantum subcapital is equal to that, this goes to 0, and then then we apply alpha of the integral over. Okay, and pretty much we are trying. Pretty much we are done. We only have to be a bit careful. So, if you're given the lemon, maybe here is a little bit of a picture. Okay, so the point is that we want a better version of F. So this is the end of that one, and the linear. So for epsilon greater than 0, set everywhere and epsilon extra is the usual smoothing of the Fourier epsilon effect. E to the minus epsilon, I guess I want to epsilon, not to epsilon. Epsilon, no, I need to by x. So that when you consider the limit of f and epsilon into 2, which is the same as the limit of f in L2, that was to 0 as epsilon to 0. And we want to show we wish to show that the limit as epsilon was to 0 of epsilon omega is equal to 0 for all omega bigger than a over 2. Because if we show, okay, so this goes to 0, and this goes to 0, and if this goes to 0 on some set, then this has to go to 0, and this is 0 on that set because the convergence implies pointwise convergence for subsequent. Okay. So So that's like this. That implies that x 0 comes everywhere. That's right. So we use lemma 2 and we get so we should show that and we simply compute. Okay, this is like the integral between minus infinity and plus infinity of f of x times e to the minus 2 by x omega e to the minus 2 by x epsilon x, and we split this into a positive term. So that's like integral between 0 plus infinity of this function here. Maybe I should have okay. Of f of x times e minus I times epsilon times epsilon times epsilon minus I omega x minus the integral is infinity of x times e to the let me go because otherwise I make mistake with the signs. F of minus x, sorry, we are in negative, e to the 2 by minus epsilon plus I omega. I don't know why, yeah, omega. X, x, which is and this one.
Sorry, I cannot read the exponent.
So this is 2 by x plus I omega. Yes. What is that? Well, this is pi 0 computed at epsilon minus I omega. Maybe here it will be done. Let me check. There was a plus. Okay. Okay, I give a reply. Yeah, there was a plus. Okay, so this is pi 0, this one, computed at I omega plus epsilon. And this is pi because we are in the negatives, computed at omega minus epsilon. But we need that Okay, suppose omega is positive. Suppose omega is positive, this is like x. So this is I omega plus epsilon, and this is omega minus epsilon. Over there. Okay, and phase zero is defined here, and phi pi is defined here. So that's what we saw before. So they're defining this aspect. Well, but we have a dilemma, and dilemma says that this very last thing is the same if pi over 2. And this is if I put pi over 2. Because the difference between this device and this device is less than pi, so we can dilemma. Okay. Which means that so instead of integrating on this line for this point and on this line for this point, we integrate on this line for both points. Maybe something. And this is supposed to, okay, but this is a function. So maybe I want to verify. Okay, I have to distinguish between T positive and T negative, omega positive, omega negative. So if I want to have this point, it's better if it's minus 5 over 2, because I am integrating over this line. So this line gives me yes. I have to make a correction to that. And this goes to 0. If epsilon goes to 0, simply because this function is orthogonal. Yeah. Okay. And so I guess that finishes the proof first. Because if this goes to 0, provided that in this case that omega is greater than or equal to 2, if omega is less than the reverse, you get 5 over 2 here. And then we have at omega is equal to 0. Okay. Maybe. Okay, 10 minutes. Let me just make a couple of comments on this paper here. Just random comments. So if you look at the proof, you can realize that okay, remember the hypothesis of Wiener were that this is an function and that as was that is bounded by a constant let's see, 5.8. Okay, this hypothesis here can be replaced by the third hypothesis that gives you some less or equal than 3 epsilon times the 5 plus epsilon and the minus second, which is that for all epsilon. So for epsilon bigger than 0, there is a constant that is opposed to its which is the weaker hypothesis that we see that all of these arguments work with their stable under this representation. We are always in open set. Second remark, well, it's not a remark, it is that, okay, what, maybe the next thing, about reproducing kernel. So PW is a reproducing kernel space. But okay, we already first lecture we saw that that was true on R, but that was true on C. In fact, we can F Z is the product of F with Z is the inner state where K Z W is A times sine whatever this sine 5A that minus W over 5 minus W. So this is the reproducible kernel. Is that I want that which is the integral between this and e to the 2 pi I z w omega omega. Okay, that's equal to the inner product between F in case where the constant where kz where this is the transform of that. So where kz X omega is the conjugate of that. It is the e to the minus 2 pi I z bar omega restricted interval. And then you compute K of Z at W. And maybe I shouldn't use anything that worked out, you know. So that equals to the integral between minus 2 of e to the minus 2 pi I bar omega, which is that times e to the 2 pi I W omega. The omega with the calculation. And when you do when you compute the norm, we did as we put that simply z to z. Okay, you do the calculation, then you get A times the hyperbolic sine of 2 pi y a over 2 pi y, where y is imaginary part. That, which is bounded by a constant times e to the pi. Right. Or, yeah. So, and instead we get okay, so from this, you immediately get the project as a corollary. According to the estimate, because this but we should work. That which is okay, but for the constant it is independent of and here you get e to the pi imaginary part. Okay. So we started with an estimate which was the estimate of f of z by e to the pi mod z times a, and we end up with a better estimate which is bounded by e to the pi imaginary part mod z. And okay, I want to do this because, well, first because it is imaginary parts, and also because this way we can better appreciate the theorem by Johann Schwarz. So theorem. Okay. Who said that the following are equivalent? One, that f is an impaired function satisfying this satisfying this estimate. Well, maybe there is something that was equally pi k set, and maybe there's a constant for some. And so all functions that we find this estimate without a two hypothesis are expecting the Fourier transform are accepting the Fourier entire transforms of a distribution where T is a distribution okay, we can take the solution, with this support on E minus A over 2. And in fact, okay, I don't expect everybody to know about distribution. If you think of a distribution like Dirac lanterns at omega in over 2, so it's this distribution, and when you inherit Z, that's the integral, well, of course, it's supported over there, of e to the I omega Z here and there of Z, which is exactly e to the 2 e omega 0 Z, omega I omega 0 Z. So, and in fact, this satisfies this estimate that. And if you consider, I don't know, the derivative, let's say n derivatives of that, then you get which is like first derivative is like what the range parts for the dipole plus infinity on one face of the point minus infinity on the other face of the point. So we take any derivatives, then you get you have that, then you get 25 on the and the derivative. And integrating by parts, which is something you can do in distributions, integrating by parts and times, it means that you're taking minus 1 to the n and derivatives of that multiplied by that n times that, which is like the power that. If I can still use second, oh, the space has no multiplier. That was maybe. Cornelius talked the length was important multipliers, and this space has no multiplier because well, basically this space can that much because okay, so the multiplier space of the beginner is that constant. The idea is that if m is a multiplier, then 1 m is bounded, 2 m is the homomorphic. It is a homomorphic because I want that because I wanted this function here is a hormone. Right? And this function doesn't have many zeros, so I can choose for each z0, I can choose a neighborhood of z0, and I can choose a w, so that this is not 0 here. So I have the product of this and a horomorphic function which is vanishing, is horomorphic, and this has to be horomorphic. So it is a horomorphic, it is bounded, then it is constant. And as a consequence, it is that without well, if you have by linear algebra, you can interpolate 3 points by functions in space. But you cannot even interpolate 2 points because there are no multipliers and in a big space. You can interpolate by function. The end of the story. Okay. Have a nice weekend. No, have a nice
Ciao Nicola.
Ciao. Ciao Luca.